Want to introduce Chris Guikema from DornerWorks. So he's going to talk about experience improvements and optimization, and hint, it's going about virtio and how to use it. So Chris, the stage is yours.
All right, thanks for the introduction, Axel. So first, this is a 15-minute presentation. I could probably stretch this to an hour if I needed to, so we're just going to breeze through some of this stuff. So starting with common use cases. Haven't heard it so much at this summit, but last year's summit, one of the very common use cases was taking existing functionality from a legacy system, wrapping it into a virtual machine, and then creating seL4 threads. And bam, you have a system running seL4 with the isolation properties, and you can infer some security properties from that. A second common use case is a cross-domain solution where you have two VMs. One has secure properties, the other is just simply a general purpose VM, which has no security properties. However, given a lot of this time, the functionality was previously all contained in one Linux machine. You have to start wondering about the communication paths between the secure and the general purpose VM. So that is where virtio-net comes into play. So what is virtio-net? We've had a topic already about virtio, so everyone should be fairly familiar, but it is a software implementation of a network device. The benefits of this basically come from the fact that you can leverage the existing network stacks to communicate between VMs. And it's also a protocol, so it's not Linux specific. Other operating systems support virtio-net, so you're free to choose whichever one works the best. So a little bit of an overview here. How does it work? Well, the host, in this case, implements a virtual PCI bus, and on that PCI bus, there is a virtio-net device. The guest, during its initialization process, scans the virtual PCI bus and loads a virtio-net driver. And then, surprise, surprise, you have, when you do your IPA or IF config, there is an ETH0 device, and it has its own MAC address, and you can use it like any other standard hardware network device in Linux. From the host perspective, the host, as I mentioned previously, implements a virtual PCI bus, and on that PCI bus, it provides a virtio-net device. When the guest accesses that PCI bus, execution is trapped from the guest into the host. Now, the host knows where the network packet is stored in memory. It's in a vring, and what it can do is read the first 6 bytes, which is the destination MAC address, compare that to any MAC addresses that are in the system, and place it in a vert queue, and then send a nice notification to the other side, the destination, basically says, hey, you've got a packet. The host can read the packet from the vert queues and place it into the destination in guest memory where the guest is expecting the packet, and inject an interrupt to the guest to let it know that, hey, you have a packet available, and then the guest can pass that packet on to its destination. So this begs the question, how well does it work? Well, if you need to just communicate between two VMs, pings, status updates, simple communication path, it works great. However, if you have a throughput-focused application, the performance is not ideal. So this test setup is 2 VMs, each are pinned to their own core, and I'm running iPerf3 on one VM, or on iPerf3 on both sides. One side's the client, one side's the server, and we are getting approximately 50 megabits per second. So, obviously, we have customers who have throughput requirements, and we talk to them and we say, hey, here's a communication channel. They go, how fast is it? We say 50 megabits per second, and they say, try again. So obviously, we need to start going into some debugging mode here. And we found the problem is basically that guest memory access in the VMM is very slow. So the upstream methodology, 1, you find the physical address to read from. That, if in virtio-net, is in the descriptors. 2, you find the capability associated with that page. 3, you use the capability to map that page into the host's address space. 4, you read and write the information using that page. And 5, you unmap the page from the host's address space. So that begs the question, how often does the host need to access the guest memory to send a packet or to send and receive packets? The answer, a lot. So in the emulation layer, there are 4 functions. These are all available on GitHub. I don't know how well you can see them, but the first one is ring avail, that reads guest memory once. Ring avail index reads guest memory once. Ring desk reads guest memory once. And ring used add reads guest memory once and writes guest memory twice. All these functions are critical for virtio-net to work. So we can't get around to not using them. And on the transmit path, there's this emul notify tx function. It makes one call to the ring avail index, ring avail, and ring desk function. And then there's one direct read of guest memory to get the network packet. And then after that network packet has been read from the guest memory, there's one call to ring used add. So all in all, we have 7 maps and 7 unmaps. On the receive path, the callback function is emul rx complete. There is one call to ring avail, one call to ring desk, and one call to ring used add, and one direct write of guest memory to give the guest the network packet. So again, 7 maps, 7 unmaps. So, begs the question, can we speed this up? And the answer actually lied in an old x86 library implementation. We had a customer who wanted multi-core x86 guests. We had previously open sourced a 64-bit version of that. They wanted newer seL4. And when we rebased the multi-core implementation, we were getting random guest data access faults. Looking into that a little bit, we realized that x86 VMMs were mapping and unmapping pages simultaneously, so there became a time where one guest was using a page right before another VM unmapped the same page from the same vSpace. So, looking back at it, the old x86 libraries had this concept called a translation vSpace, where each page of guest memory remains mapped to the host at all times. Essentially, when you want to read a page of guest memory, you look up what that physical address, and it returns the virtual address that the host can use to read the page. And the question is, how does this help? So after implementing it, the throughput improved by around 8 times. So we went from 48 megabits per second all the way up to 380, which looks pretty good on a bar graph there. But, you know, the old Spider-Man quote, with great power comes great responsibility. With great throughput comes more bugs. So increasing the throughput introduced a number of bugs that weren't seen at lower speeds. Some of them were simple to fix. More data going through the vert queues meant that the vert queues were running out of space rather quickly. So what do? You just increase the vert queue size, problem solved, easy. Others, not so much. When you were running these iPerf tests over a long period of time, we were clobbering the cache, and then what we were seeing is descriptor corruption. So the actual data path would break from one side, but would work on the other side. That was a real problem to fix. So I guess the next portion here comes to optimization. That's part of the topic here. So each one of these arrows represents one copy that the system does. So the packet gets copied from guest memory into the emulation layer. Then the module layer copies the packet again. And then finally it gets copied into the vert queue, and then it works in reverse on the receive path. So just looking at this, there are probably a few of these mem copies that just shouldn't exist. So very simply, we were able to remove the mem copy from the emulation layer to the module layer, and we're able to see an additional throughput increase from 380 up to 522 megabits per second. That was pretty nice to see. We did some additional testing with trying to reduce the mem copies further from 3 to 2. And that also improved throughput, but also reduced stability by quite a bit. So I didn't include those results in here. And so with all that said, we have to think about what's next. Well, we open sourced the translation vSpace commit. I know for a lot of people it's not ideal to have the guest address space always mapped into the host address space, but what it does show is that guest memory, reading and writing guest memory is slow. And if you have a throughput focused application, that's one way. If you can always have those pointers mapped into the host memory, it will speed up your system by quite a bit. And, you know, because we're a services company and I'm giving a presentation, I have to do some form of sales work here. We also developed a further improvement that is available for purchase, where we got the throughput up to 1.5 gigabits per second between VMs. And yeah, looks pretty good on a graph. So thank you. That's all I have. If anyone has any questions, I'll be happy to answer.
Thanks, Chris, very much. So any questions? We have 2 minutes.
Do you know what I should expect as the performance on native Linux? I have no idea what it would be.
virtio is between two, I guess, Linux guests, so I don't really know how you would. Yeah, I haven't really done any testing with that, but I would expect near gigabit performance. I know on Zen it's about a gigabit and a half. So.
Okay, any more questions? Well, it's good. Then we stay on time. Then thanks again, Chris, for this interesting talk.